Welcome back to Honors Calculus. In this video, we're going to start into Lesson 5, Continuity on an Interval, with the idea of completeness. Remember, from earlier in the course, we defined the real numbers as the complete ordered field. So far, we've only used the properties of a field, the commutative, associative, inverse, identity, and distributive properties. We've used the idea of an ordered field, an inequality that exists on that ordering. And as we saw, the rational numbers are an ordered field just as much as the real numbers are. So we haven't done anything yet that has precluded us from working with just rational numbers. We haven't given a justification yet as to why we need something more involved than the rational numbers. The definition of the real numbers said that they were the complete ordered field. So in this video, let's examine what that means. Let me get my head out of the way and talk about a little bit of vocabulary. Let's let S be a subset of, well, I'll use R here because we know that the field we're interested in is the real numbers. But let's assume that R here represents any field, and this definition still works perfectly fine. We say that the set S is bounded above if and only if there exists some, I'm going to call it a capital M in R, such that for all x in S, x is less than or equal to b. So not b, capital M. Right. So the set is bounded above if this M exists, and we call this M an upper bound of the set. We also have a lower bound and bounded below. All right, let's call the lower bound a lowercase m. All right. So if you can find this little m so that every value of x is greater than or equal to little m, then we call little m a lower bound on the set, and we say that the set is bounded below. In general, if I learn how to write we'll say that a set S is just bounded if it is both bounded above and bounded below. One thing that I want to point out about this definition, kind of the weakness of this definition, is that all we're saying is that the property holds. We're not saying anything about how well it works as a bound. Right. Consider the set 0, 5. This is a bounded interval. When we talked about interval notation, we said that an interval that did not have an infinity on either side was called a bounded interval. And now we've finally gotten to what we mean by that. From the definition, remember the interval from 0 to 5 is the set of all real numbers x such that 0 is less than x and x is less than 5. So clearly from this definition, for all x in 0, 5, x is less than or equal to 5. So 5 is an upper bound on 0, 5. But it's not the only one. Right? It's a subtlety in the definition. Every value in the set is smaller than the upper bound is not the same thing as everything smaller than the upper bound is in the set. So 6 works as an upper bound on 0, 5. It's not the smallest one, but it is one. 7 works, so does 12, and 15, and 768, and 25 pi squared, and the square root of 993, which I don't think works out evenly, but I don't really know. Right? There are several upper bounds for any set, and there are several upper bounds, infinitely many of them, for any lower set. Right. One thing in math where the name does exactly what you think it does. The least upper bound is the smallest of all of the possible upper bounds. For any upper bound, everything larger than it is also an upper bound. For most upper bounds, there are at least some upper bounds which are smaller. The least upper bound is the one for which there are no smaller numbers that are also upper bounds. Right. We will denote the least upper bound of set S as LUB. I've heard people call it the lub. I don't recommend it, but I've heard people say it. Some textbooks also call this idea the supremum. So you might also see this called SUP of S. It all works the same. I'm not going to be that picky about it. I prefer least upper bound. That name means more to me than supremum. But if you're going onward to further mathematics, you'll see the idea of supremum more frequently. We also have the converse of this, which would be the greatest lower bound. The lower bound, which is the largest among all of the lower bounds, which we'll call GLB. And again, if you're going on to further math, you'll also see this called the infimum, INF, but that name is mostly meaningless. So let's stick with calling it the greatest lower bound, or GLB. It's a lot easier to remember what that thing's supposed to mean. We say that an ordered field is complete if and only if every bounded set has a least upper bound and a greatest lower bound. And in fact, even more specifically, every set that is bounded above, whether or not it's bounded below, has a least upper bound, and every set that is bounded below, whether or not it's bounded above, has a greatest lower bound. So for example, consider this set S. I'm constructing this set by further decimal expansions of the number pi. 3, 3.1, 3.14, 3.141, 3.1415, 3.14159, 3.14159.2, 3.1415926, and so on, and so on, and so on. We could be here all day. Clearly, in the way that I've listed this, the entries are getting larger and larger and larger. But there's a stopping point. Every entry is smaller than pi because I'm truncating it, not rounding it. So I'm never rounding up, always rounding down, which means that every single one of these entries is below pi. And in fact, if you keep going, I think it's fairly clear that the least upper bound of this set is going to be pi. And I use this as an example because every single element in this set is a rational number. They can all be written as fractions because they are all terminating decimals. But the least upper bound is pi, an irrational number. So this example shows us that you can have a set entirely made of rational numbers, where the least upper bound of the set is an irrational number. And that's why the rational numbers are not complete. The real numbers we define as the completion of the rational numbers. All right, so if we call the real numbers the completion of the rational numbers, what I mean by that is that the real numbers are the set of the least upper bounds of sets S such that S is a subset of the rationals. So take a subset of rational numbers, find the least upper bound of that set, and put that in here. Now, clearly, if you have a singleton set, a set with just one rational number in it, the least upper bound is that rational number. So we get all of the rational numbers in the real numbers along with everything else. And essentially, we construct all the sets the way I did here with this set, which is how we define pi in the real numbers under this definition. We take the sequential decimal expansions of pi, and terminating at each point, we put those all in the set. So the least upper bound will be the complete infinite series, infinite decimal expansion, non-repeating nonsense that is pi. And that way, pi is a real number, even though it cannot be written as a fraction. One of several ways of defining the real numbers. We use this way of defining them in this course because that's what's going to be useful to us. All right. And with that, we have defined the real numbers. We now know what it means to be complete. We know what it means to be ordered. We know what it means to be a field. We have all of the tools we need for talking about the real numbers. All right, let's talk about a set of real numbers. Since we just defined the real numbers as being complete, we know that S has an upper bound. We could prove, it's not really worth the effort, that if a set has an upper bound, it also has a greatest lower bound. So LUBS and GLBS exist. Let's write this sentence in order. We say that S is closed if and only if LUBS and GLBS are in S. We say S is open if both the least upper bound and the greatest lower bound are not in the set. And remember back when we were talking about interval notation, we said that a closed interval is one where both endpoints are in the interval. An open interval is one where neither of the endpoints are in the interval. And then you have the mixed intervals where one endpoint is and the other isn't, which is neither open nor closed. This definition is a generalization of that rule. If the extreme endpoints are in the set, we call it a closed set. If they're not, we call it an open set. And I guess we should also point out here that the least upper bound of an interval AB is B, and the greatest lower bound of an interval AB is A. And whether we close the interval or not, that doesn't change those things. In a closed set where least upper bound and greatest lower bound are in the set, we call those things the maximum and the minimum. Maximum and minimum are things that probably make a lot of sense to you as descriptions of a set of numbers. The distinction between maximum and minimum and least upper bound, greatest lower bound is that the maximum and minimum must be in the set. The least upper bound and greatest lower bound might or might not be in the set. But if a set has a maximum, the maximum is the least upper bound. If a set has a minimum, the minimum is the greatest lower bound. And by speaking about least upper bound, greatest lower bound instead, it saves us from the headache of if this thing is in the set or not. Just makes life a little bit easier for us there. All right. So that was a pile of vocabulary to throw at you. I want to leave you with an interesting question. Consider a set S, subset of the real numbers, so that the least upper bound of S is 5, and the greatest lower bound of S is 0. Clearly, S being the interval from 0 to 5 works. And you can do this with any interval, right? I could do the closed interval from 0 to 5 and the mixed open and closed intervals. Right? Can you find a different set? A set that is not simply one of the 4 intervals from 0 to 5, where the least upper bound of the set is 5 and the greatest lower bound of the set is 0. There are infinitely many of them. If you can find any one, then you probably understand what's going on. There are 2 major classes of them that I'll be happy to talk about in class, but I want you to spend some time thinking about that. And I'll see you in the next video.